Hey everybody, it's Dr. J, and today we are talking about molecular orbital theory. Let's talk chemistry. Alright, so we talked about a couple different theories before. We talked about Lewis structures, we talked about VSEPR theory, and then we talked about valence bond theory. And so far, valence bond theory has been probably the most detailed theory, the one that's able to predict the most. It was able to predict bond lengths or bonding schemes for the most part, and it's better than Lewis structures. However, right, there are some problems with valence bond theory. So, here's a problem with valence bond theory. All right, so valence bond theory is assuming that electrons are going to be localized on your orbitals. Okay, and it's not taking into account delocalization. So basically, right, that's double bonds, triple bonds, right, when those electrons are moving around in the orbital. Okay, as well as it doesn't help if you got unpaired electrons, right? So valence bond theory does not do a good job as far as describing that. And then there's still some other properties that valence bond theory just can't predict. Bonding energies or even magnetic behavior, right? But guess what theory can do that? Molecular orbital theory. Yes, a new one. It's a new theory, everybody. You should have known. So, molecular orbital theory. Basically, think of this as the most advanced theory of them all. You're actually just going to be introduced to this. This is a very complicated theory. The whole class is really dedicated to this. I'm not talking about Chem 1. I'm talking about like there's a whole class just talking about molecular orbitals. So, molecular orbital theory. Basically, that's going to apply Schrodinger's wave equation to the molecule in order to calculate those molecular orbitals, right? And because of this, we're now developing orbitals for the entire molecule now, right? And that's including those delocalized type of electrons as well. So each molecular orbital will be able to hold two electrons of opposite spins, as well as your shape of your molecular orbital will be representing the probability of where your electrons are. Okay, we have linear combination of atomic orbitals or LCAOs. All right, so basically these are the weighted linear sum of valence atomic orbitals of an atom in a molecule. So basically these are all the atoms in a molecule. Like I mentioned before, these are the orbitals that they're technically called. Okay, so these orbitals, remember, are wave functions, and the waves can combine either constructively or destructively. So now it's all full circle, right? When we talked about destructive and constructive, right? Because those wave functions, they actually can be applied as orbitals now. So we have two types of orbitals. We have bonding molecular orbitals and anti-bonding molecular orbitals. So bonding molecular orbitals are formed when the wave functions are combining constructively. Okay, so basically, those molecular orbitals are going to have less energy than the original atomic orbitals. All right, so most of those electron density is going to be between the nucleus. All right, and you're going to see sigma and pi for these type of bonding orbitals. And we also have anti-bonding molecular orbitals. So this is formed when the wave constructions are combined destructively. Okay, so basically, these orbitals are going to have more energy than your original atomic orbitals. So most of the electron density is going to be outside the nucleus. Okay, in which case we can have nodes in between those nucleus. So to symbolize these anti-bonding molecular orbitals, we use what we call sigma star and pi star. This is basically, right, a little example of how they're looking, right? Destructive, we understand that they're going to be combined to these anti-bonding molecular orbitals here. So once again, we're combining our 1s orbital here, and then we're going to get our sigma star 1s orbital. Constructive, we're combining both our 1s orbitals, so we're going to get a sigma 1s orbital for our bonding molecular. Okay, and then basically, this is what it's talking about with the antibonding having more energy than the bonding orbitals as well down here. So, of course, let's look at an example. Hydrogen. Here's a hydrogen molecular orbital. In this case, when we're talking about these molecular orbital theories, we're combining the atomic orbitals to form our molecular orbitals. So in this case, we got to know hydrogen's electron configuration, which is 1s1, right? So 1s1, that means that we're going to have one electron in the 1s orbital spinning up. So we see this here. and this hydrogen and the hydrogen over here. But when the hydrogens come together to form our H2 molecule, this is where we're going to form our molecular orbitals, okay? So once again, we're just taking our atomic orbitals and combining them together to form these. So this is essentially how your setup is always going to be, right? You're going to have your sigma 1s orbital on the bottom. So this is your bonding orbital. And then you're going to have your sigma star 1s orbital on the top, right? Because anti-bonding is going to be more energy than our standard. And then our bonding is lower energy than our standard, right? That's because, right, lower potential energy. When they come together, they're more stable. Anti-bonding is going to be higher energy. So once we have our setup correct, right, with our sigma 1s molecular orbital and our sigma star 1s molecular orbital, then we just fill them in, right? So in this case, I have 2 electrons, so I want to fill in my bonding molecular orbital first. 1 electron spinning up, 1 electron spinning down. And this is letting me know that I have 2 electrons in my sigma 1s orbital for my H2 molecule, with no electrons in my sigma star 1s molecular orbital here. So a little break in between before I do another example. Let's talk about bond order. Bond order is the difference between the number of bonding electrons and number of anti-bonding electrons divided by 2. Okay, so we only need to consider the valence electrons whenever we're talking about bond order. So they may be a fraction, and that's okay. All right, so essentially we understand this trend, you're good. The higher the bond order, the stronger and shorter the bonds. Okay, that's essentially it. Okay, and if you got a bond order that is 0 or negative, then a bond is unstable and probably does not exist. Okay, so no bond will actually form if you have a bond order of 0 or negative. So essentially we're using this equation here, right? The number of bonding electrons minus the number of anti-bonding electrons divided by 2. So for example, let's say that we're looking at H2, right? So if I got H2 here, what we're going to see here is, like, for example, we're going to take the bonding electrons. So in this case, the bonding electrons are going to be in my molecular orbital, that is my sigma 1s. And we're going to subtract that by the anti-bonding here. So in this case, for H2, right, if we go back to H2 real fast, the bonding order is bonding electrons minus antibonding. In this case, I have 2 bonding electrons minus my antibonding, which is 0, divided by 2. So 2 minus 0 divided by 2 is going to be 1, right? So this is telling me that I have a bond order of 1, which in this case is going to tell me that I have a single bond strength, right? Clicking, there it goes. The bond order tells me my bond strength, right? So let's look at another example. H2, in this case, is an anion. So we draw the molecular orbital for it. I'm going to have 2 electrons in my sigma 1s, and then I have 1 electron in my sigma star 1s. Now, real fast, let's review this quickly, right? In this case, I'm going to have extra electron. So I have my 2 electrons here, but I have 1 more extra electron. So I have 2 electrons in this 1s, and then 1 electron here. So I'm going to have 2 in my bonding, 1 in my antibonding now. So that's going to impact my bond order, right? So it's going to be 2 bonding electrons here minus my antibonding electrons here. So 2 minus 1 is going to be 1 divided by 2. It's going to give me 0.5. So this is still a positive number, so it still can exist. So it actually has a bond strength that's going to be less than a single bond strength, but it's stable. Okay, so this can technically exist. If we have helium, right, helium-2. So we're going to draw our molecular orbitals. In this case, helium has 2 electrons in the 1s2, right, for both cases. And then when it comes to doing our bonding, right, it's going to be sigma 1s, sigma star 1s. So notice, right, it's always going to be the same here. It's just depending on how we fill them. So in this case, we got 4, 1, 2, 3, 4. So we're going to fill up my sigma 1s molecular orbital. Then we go to my antibonding, sigma antibonding 1s orbital here. And then what do we do to find a bond order? It's going to be the number of bonding electrons 2 minus the number of antibonding electrons, 2. So 2 minus 2 is 0, divided by 2 will be 0. So in this case, this is actually not stable. It actually does not exist because we understand that helium, once again, is not a diatomic molecule, right? So in this case, it actually exists as a single atom, okay? And this is, this is a great thing about this molecular orbital theory. We can find out a lot of information from it. So of course, I'm going to do another example for you guys. Let's do lithium Li2 molecular orbital. So we understand that lithium is a 1s2, 2s1. But we're only going to use a valence electron. So in that case, we're only using the 2s1. So we're not using the inner shell, right? Do not use these when you're doing your molecular orbitals. That's a key thing here. So we're only using one valence electron. So the 1s orbital is core and cannot be reached for bonding. So therefore, valence electrons, 2s1 there. So when it comes to drawing the shell, right? In this case, we're using the valence electrons that are in the 2s. So that's why we see 2s here, right? 2s, 2s with our 1 electron in our 2s shell, 2s shell. And then how are we setting up our molecular orbital? Well, we have our sigma 2s and then our sigma star 2s molecular orbital, right? More energy, lower energy here. And then we're just going to, what are we doing? Fill in our orbitals. Both of the electrons in this case are going to go in my bonding 2s orbital, right? So it's going to look like this for our Li2 molecular orbitals, right? And then this is just showing the molecular orbital shapes, bonding, antibonding here. Now the bond order, if we want to find out the bond order, essentially all we have to do is do our 2 from our bonding minus our antibonding, in this case none, which is 0, divided by 2, so we're going to get 1. So this is a very stable, it's stable in this case, of a bond order of 1, so a single bond strength. Now, if we want to say the molecular electron configuration, we can actually do that. In this case, the electron configuration is literally just the electrons in whatever molecular orbital shell. So in this case, if I wanted to say the molecular electron configuration, it's just going to be sigma 2s, 2, right? Standing for 2 electrons in my sigma 2s molecular orbital. Now, Li2 is stable, but in this case, it actually only occurs as a gas, all right? But it does exist, right, based on this theory. So, of course, right, the more electrons we get, it's probably going to get a little complicated, right? So let's talk about B2, boron, another example. So with this example here, you're going to do the same thing. You're going to use your molecular orbitals, in this case, to generate a 2p atomic orbital. So here's our electron configuration, 1s2, 2s2, and notice now we got an electron in a 2p orbital. P orbital molecular orbitals are going to look something like this, right? In this case, we're going to have our antibonding and our bonding, so still the same concept of forming both of these. But with pi, we understand that now we got some pi bonds, right? Because now we're into the p orbitals. So let's actually do this B2 molecular orbitals together. So here's our B2 molecular orbital diagram. So what we have here, once again, we're going to have those 2 electrons in our 2s shell, and then we got our 1 electron in our 2p. So in this case, because it's a homonuclear diatomic molecule, so once again, homonuclear, in this case, it just means it's the same atom. All right, diatomic is 2 of them. Okay, so B2. Like I mentioned before, it's going to be 2s2, 2p1, and we're drawing it like this. So notice, right, let's start out with this down here. So we're going to start with our 2s shells, right? In this case, our sigma 2s molecular orbital and our sigma 2s star molecular orbital. Now, got my 2 electrons here, 2 electrons there. We're just filling it in. We got 4 in total, so I got 2 here and 2 there. Same thing that we've been doing so far. The only difference now is right, we have to add a new orbital, p. So now we got to take into account this extra electron in my p and my 2p. So what does that mean? Well, we got a new, right? We got a new molecular orbital now. So specifically for this p, we're going to have to draw our 2, right, a 2p. So in this case, it's sigma 2p followed by our pi 2p, pi 2p, pi interbonding 2p. So right here, we have 2 here, and then we have our sigma 2p star here, interbonding as well. And then we're just filling in our orbitals. In this case, we only have 2 electrons, so those 2 electrons are only going to go on my sigma 2p orbital here. So once again, each orbital can only hold 2 electrons, okay? And if we want to figure out the bonding order, well, it's the same thing. We're going to take our bonding electrons minus our interbonding. So in this case, I have 2 electrons in my sigma 2s, 2 electrons in my sigma 2p. So these are both my bonding molecular orbitals. So I have 4 in total, but I also have 2 in my antibonding. So that's 4 minus 2 divided by 2. That's going to give me 1. So this is a stable diatomic molecule. So what it does is this, all right? And this is how we're going to be drawing our molecular orbitals. Now let's talk about bonding in homonuclear diatomic molecules. In this case, let's talk about the order of them. So the order has actually been determined thanks to computers. All right, so you guys don't really need to figure out the order. We already know the order. All right, so there isn't no single order that's going to work for all molecules. And because of this, right, this is going to impact the different orders you have to use for certain molecules. In this case, it's due to the way that our 2s and 2p are actually mixing together when we have these. But essentially, if you know the orders for these, you're good. All right. So when we have boron, carbon, and nitrogen, right, the 2s, right, molecular orbitals are always going to be the same for both instances, right? Sigma 2s, sigma star 2s, right? Always the same in this case. The only difference now is the way our p's are. So in this case, right, for boron, carbon, and nitrogens, you're going to have your pi 2p molecular orbitals as the lowest energy, followed by your sigma 2p, followed by your antibonding orbitals. In this case, your pi star 2p orbital, then your sigma star 2p. Okay, and this is only for boron, carbon, and nitrogen. Now, if you have your oxygen, fluorine, and neon, notice that your 2s is still the same, sigma 2s, sigma star 2s, right? It's still the same. But the key difference here is your bonding orbitals, your bonding molecular orbitals for your p's. So instead of having pi 2p's, you're going to have sigma 2p and then pi 2p here. Okay. Then for your antibonding, it's still going to be the same. Pi star 2p, sigma star 2p. All right. So the only difference between the two is these two over here. All right, either your sigmas first or your pi's first, depending on if you have boron, carbon, and nitrogen, or oxygen, fluorine, neon. Okay, so if you remember this, you're good to go for your homonuclear diatomic molecules.